All right, this is something a little different. And when I say a little different, I mean pretty different from anything else we've discussed so far. Although perhaps not that different. And that is sort of a metaphysical discussion of what the implications of quantum mechanics are, especially for quantum computing. So, honestly, I think a lot of times people writing in certain fields of quantum mechanics would be better off recognizing they're just doing philosophy and just embrace it, but that's neither here nor there. So, the first thing that I want to talk about is the nature of the wave function. So, when we have a quantum mechanical system, consider a electron, right? It's described by some wave function, right? And this, if you have this electron in some atom, right? This is the 2p orbitals right here. Let's see if I can, right? This is the 2pz, 2px, 2py orbitals. So there's 6 electrons here, one electron in each of these. And you'll see these drawings all the time in any chemistry textbook even basic chemistry textbooks will have these orbital diagrams. So what's the explanation here? And so this is really a fundamental question about the nature of reality is what is an electron? And I'm going to be borrowing a lot. This is not necessarily all original ideas here. Throughout this video, I'm not going to like cite my sources perhaps, or like put inline citations, but a lot of this is going to come from my readings of Tim Maudlin, who wrote a lot about metaphysics and science, and John Wheeler. I think John was his first name. I know his last name's Wheeler. Now I forget his first name. John Wheeler, yeah. Rolf Landauer and Paul Davies. So just so you know, if you're looking for more sort of information on this. So the first thing I'm going to ask you is basically if anyone's looking at this, right? The question is, if you see this little diagram and I say, okay, let me draw it out. Let me zoom in. So this right here, let's be even simpler. I should actually check what the diagrams are. I don't have all the diagrams memorized. Oh yeah, I thought it was just a sphere. Yeah, so this is our little 1s orbital, right? So we have a hydrogen atom and we have its little electron. So, right, this is just a proton and an electron. That's all a basic version of hydrogen is. So you see it's a little sphere, right? If we drew this out, this would be our little proton in here. This would be our sphere around it. And we'd say that's the electron cloud is sometimes the terminology that gets used. And you can describe it using a wave function that you decompose into radial and angular components that everyone who's taken a quantum mechanics class will do. But the question then that I'm going to ask is, what is the electron here, right? So I'm giving you a probability, well, not distribution, but density function. That's the word I'm looking for. So if I'm saying, the electron is, as we typically conceive it, right, the concept of matter, and this is something that there's a lot more metaphysical writings on, is an electron is a basic unit of matter or material. It possesses some mass, right? So you think about, you stack a lot of electrons on a scale, it'll weigh something. So is the electron here, I'll maybe help elucidate the question by providing two potential solutions. Is the electron actually in one place here? And this is a representation of our basically lack of knowledge. So the electron, so that there's some probability that it's going to be in any given place, but it is actually only in one of those places. Or is it actually the electron itself is spread out across that entire existence, right? So if I say, what is an electron? You'd say, this sphere right there that has a proton inside, that has different, there's some density gradient there. That's what an electron is. So you might say, okay, an electron is what it is. It doesn't matter. But this is really, a foundational question about reality is what is the basic unit of material? If an electron is some subatomic particle that, as far as we know, you can't decompose it into more and more subatomic particles, although maybe you can, but the limits of our physics understanding, what is an electron. And so we can describe it using some quantum mechanical wave function, but that doesn't really give us a solid metaphysical insight into its ontology. And so when I presented these solutions, there's names for them. So for example, this is when I said the electron is spread out, you can think of that as the matter density ontology. There's also the point. You could think of the other version as a point particle. And so then I think most people, maybe I'm mistaken, would sort of reject the idea that the electron is sort of this spread out, right, function. So, which is neither here nor there. That's just what I would predict, even though this is really sort of, right, this is our description, a visual description of the wave function. And if we're saying this electron is the wave function, then that seems to be what it is. But if you're saying, no, it's actually one of these points, and it's not like it's just somewhere around the proton, it's just that this description is representative of the information that we have about the electron, right? So if we zoom in on the electron, maybe we could, know more about its position. There's some other considerations to take into account. Specifically, right, these are all relying on the sort of basic physics concepts, but if you have your classic double slit experiment, right, where you have I'll just draw them as lines. You have two slits, right, that you're shooting a particle in, and then your detector back here. This was used, some, 150 years ago to show that, hey, if you shoot a light at it, it makes if you were shooting particles, right, you would expect to measure 2 points here where the particles are going through. But if you're shooting a wave through, right, you would assume there's some interaction and interference, so you'll get some wave pattern where you have more. That's a really terrible drawing, but you know what the two slit experiment is. So then, 100 years later, it was also suggested, I believe, by Richard Feynman in, I want to say, 1960s. He said this would also be able to show the electron wave particle duality. Not only do our photons waves and particles, quantum mechanical objects such as electrons or even larger molecules have been shown to obey this as well, have wavelengths. You could do a human, right? That's something a lot of people do in quantum mechanics classes, calculate the de Broglie wavelength of themselves running or something like that. So if you actually shoot an electron, and this has been done, I'll link, I think, the first paper that experimentally did this before. If you shoot a single electron through this, right, you would expect that, well, shooting a single electron at a time, right? If you shoot a single electron, you're going to get a single detected, right? But if you shoot many, many electrons one at a time, you'd expect that they would go through, right, one or the other. So you get two lines here. But that's not what you see. You, in fact, see a pattern just like you did with light. So what that means is that the electron, when it goes through for a single one, right, for the electron to get over here, the only way it's doing that, if it's going straight through, is that it's actually a wave and it's interacting with itself. And so the question then becomes, the reason I bring this up is because if the electron is just a point that we don't know about, that seems to sort of be at odds with also being a wave, because a wave, right, is just, you could say, oh, it's a wave packet, and maybe there's an explanation there. I'm not trying to argue for or against any position here, just present interesting ideas that I think sort of underlie our assumptions about a lot of these quantum mechanical entities. So with this idea, right, that it's a point particle, this problem of the double slit experiment becomes a lot more interesting because it also is a wave. So, you know, you might say, oh, it's also a wave. There's also some interpretations called flash or flash point, I think, ontologies, which Bell was actually a fan of, although I don't think he mentioned that by name, where basically until you know its position, right? If you're saying I have some particle that's a distribution, right, over some states here, and so I measure it and I say, okay, it's actually right here in state 2. It's not in any of those states. It doesn't, the existence is determined by the measurement, and so it exists for that flash. Basically, is the idea there. Hence the name, the flash ontology. And so there's many other interpretations. These are just some highlights, and we'll get into interpretations of quantum mechanics in a second. But when asking such a simple question, it's interesting that there's such complex results. So this is sort of, a blitz overview, but all I'm trying to suggest here is think about the nature of reality. What does the wave function mean, right? If you tell us that it's in a superposition of two states, what does that mean? Does that mean there's an electron in both of those states? Or does it mean that we just don't know which state it's in? And so when I talk about knowing, we'll get into that more in a second, but that question, I think, there's the many worlds interpretation of quantum mechanics. There's Bohemian mechanics. There's the Copenhagen interpretation. There's all these different interpretations of what that means. And so I think that's something that everyone who works in quantum mechanics or quantum computing can think about, because we can create a superposition and we can work with that trivially on anybody can on a quantum computer. You can go log into IBM's free service right now and create a superposition. And so it's physically realizable, but what does that mean physically? And I think that enlightens us perhaps to some of the limitations of our understandings of nature, in the sense that we think very much in the physical world. Not that I'm implying, I'm not arguing for some sort of dualist interpretation here, but simply that when something doesn't have sort of a visual representation, it's very hard for us to grasp, to make a mental model of what that would mean. And so it's hard to, right, superpositions thus far have been limited to microscopic objects. So that was part of the controversy over the tardigrade paper, was saying, not that the tardigrade is like visible per se, but simply that it's a substantially larger object that, they claim to exhibit these entanglement or superposition properties. So getting into the idea of information, this is becoming more popular and is especially popular, I think, in certain quantum physics fields. The idea that information is really the basic unit of existence. So typically, right, we think that we have some sort of mathematics that we derive our physics from, and then from that physics we have our information. But it's becoming increasingly popular to say we have our information, and then we have our physics that we derive from that, and then we have our actual matter. And so this is sort of a complex topic that I'm just touching on here. For anyone interested in this, I would encourage you to look at the book by Paul Davies and Niels Gregersen, Information and the Nature of Reality, in which they talk about this a little more. They have essays from different people. I believe Seth Lloyd, actually, who's a famous quantum computing researcher, has contributed to that. But nonetheless, the idea I'm talking about here is that information precedes material matter. Now that sounds perhaps obvious to some and controversial to others, but the idea is that, and you'll see this in a lot of cases, that the quantum mechanical wave function is a representation of our knowledge. So if we say, right, we can represent, and this is similar, right, to we can also say the entropy of a system is related to our knowledge of it. And so when we say, if we had perfect knowledge of the electron, right, we could say, okay, we know exactly what state it's in. And so that's equivalent to measuring it repeatedly over and over again. Now there is an interesting, I believe it's called the Quanzino Effect that comes into effect here that I recommend you read about. But nonetheless, that's equivalent to what it's saying. So the information, right, that is the wave function precedes the matter that is the electron itself. Now there is a lot of variations of it. This is not the only, so I don't want you to take this away being like everyone who says information is primary is believing in this. This is just one of many interpretations that exist. So don't take this as gospel. But it's interesting because it's becoming a lot more popular. I believe even some sort of pop culture figures have mentioned it in interviews, this idea that information is the basic unit of reality. And when we're talking about information, we can't help but also talk about entanglement. And this is something that attracted a lot of controversy and is something that to this day still attracts controversy and a lot of quack physics as well from random people. But the idea of entanglement, and so this is something that troubled Einstein, supposedly. He said that God does not play dice with the universe. Niels Bohr responded to that by saying Einstein stopped telling God what to do. But the idea that we're going to be transitioning here, this is sort of transitioning back into the idea of the wave function and the nature of reality, right? Let's suppose we have our little wave function, and this is something we can create on our quantum computer, right? Let me normalize it. So this is our wave function, right? This is a classic Bell state. Einstein thought that if we separated this, right, we took, so this is Alice and this is Bob, right? This is Alice's qubit and this is Bob's qubit. And we took them and they ran to 1,000 miles away. And then Bob measured his qubit and Alice measured her qubit. And they would always get, right? You would always get 0, 0, or 1, 1. Einstein thought that what they would measure was determined upon the creation of this entanglement, that basically that it's not actually random because this creation was determined when the result was determined upon creation. And this is actually the source basically of the Epr paradox, and this is why sometimes you also see this called the Bell state, the Epr state, not just the Bell state. But the problem there is that is experimentally false. You actually can show, and you can read about Bell's inequality if you're not familiar with it, that by measuring in different bases, you can confirm that these measurements are actually not determined upon the first creation of the state. And basically that just comes from classically, if you sample something that's independent, then you can measure it in different bases, right? So if you're saying, okay, it's determined once this is created, then if you measure it in different bases, then there's going to be some probabilistic properties that have to be met. And so You can just, it's a really common, I guess, I would expect most people to have heard of it, but if you haven't, there's lots of great resources for explaining more. But going off of that, now this is where there's a common sort of misconception, right? Is that this will somehow enable faster than light communication. And that's not possible for, I mean, the simple reason, right? And this ties into information that if Alice, there's no like information passing scheme. If Alice measures her qubit 0, and that means, right, or she does something to upon getting 0, right, or there's some information associated with the 0 state, she has to actually send that to Bob classically, right? So Bob also measures 0, but he doesn't necessarily know what that means because this is just a random, right? It's like a coin flip. So there's the classical information still has to travel anyway, slower than the speed of light. There's also 1,000 articles online about why entanglement doesn't allow for faster than light communication. And this is something, now here I'm going to talk about something that I'm less knowledgeable on, but this is where the nature of information and observation becomes confusing, right? Because if I did this, right, let's take our little qubit, we have it entangled. I'm just going to represent it as an A now. So we have qubit A that's in this superposition entangled with qubit B. We separate them. There's a non-trivially physical connection, right? So if I separate them and I, cut between them, I put a little guillotine and I chop between them, that doesn't change whether they're entangled or not. If they're in little boxes and I separate them, obviously this would be hard to do because of the finickiness of particles, but think in a theoretical sense for now. If I put them in little boxes in a vacuum and separate them by a billion miles, and then I don't know, I blow up 1,000 atomic bombs in here, right? These will still, that doesn't, assuming they're shielded from all of these effects, that won't influence it. So there's some sort of interesting connection there in the sense that I think, right, now if someone's like, oh, that will actually, even in a theoretical sense where these are completely isolated from those effects, if I'm wrong, then feel free to correct me. But there's that connection that's still there that's very interesting. And even though it doesn't allow for faster than light communication, there's still something that that correlation is still instantaneous. So this is an experiment I'm pretty sure has been done before. If you create this state, you separate the particles and you say, okay, we're going to separate them by, we can't do a billion miles obviously in real life, but separate them by, I think this was recently done by a team in France or last year or something, by like 49 miles. Separate them by that, measure this, say, okay, I'm going to measure this state at, time 0, t equals 0, and I'm going to measure this at t equals 1 times 10 to the negative 10th, right? So this is going to be, there's not enough time for light to travel 49 miles, or I don't know if there is in this example, you might have to lower that time. You're always going to get whatever this result is. That correlation will always be true. So there is something happening in the sense that no matter what, this outcome correlates faster than light travels. Now, that's not saying that it travels faster than light travels, but there's something here, I think, that is very essential to understanding what's going on with these particles that happens that we currently don't have a great sort of metaphysical grasp on. What exactly, is entanglement, or what is superposition too? These are concepts that we have great mathematical descriptions for and great analogies for, but we lack the same sort of, because they're microscopic, we lack the same sort of macroscopic metaphysical understandings. And so that's basically just an interesting idea that's and problems that have come up in that a lot of people probably experience in their learning of quantum mechanics. I'm not, this was just sort of a rant slash high level overview that I just hope to inspire some more questions and some more discussions. I'll link some relevant reading below. I should also, I don't know if I mentioned this, but on the information concept, it was John Wheeler who said, who had the statement "it from bit." So material from, right, it being existence, material from bit being, information. That's just tangential, but I'll link some of the ideas below that you can read more on that. I don't know, this was a lot less organized than I thought it was going to be, so there's just 26 minutes of me rambling about metaphysics in a somewhat coherent way, hopefully.